Hello, my name is JIAHUI STELLA Lee, and this is the video journal for me and Professor Miller's bounding vanishing at the central point of Cuspidal Newforms. To begin, I'll give a brief overview of our work. Our central research question was how to improve upper bounds on the order vanishing of L functions at the central point. Past literature typically obtained better bounds by computations through higher level density. We investigated the problem from a slightly different angle. Specifically, we improved upper bounds through computations using the fourth centered moment. The family of L functions we study is the Cuspidal Newforms L functions. We assumed a generalized Riemann hypothesis so that we could order all the zeros in one line and study statistics like the n-level density and the n-centered moment. For our computations, we used test functions to capture the local behavior of L functions at the central point. The direct delta function is theoretically the most optimal test function because it is very concentrated at one point, but its Fourier transform has infinite support, which does not satisfy our restrictions for calculations, and hence we needed to find good approximations to the direct delta function. This is the definition of the n-level density. Since the test functions are rapidly decreasing, the contribution mainly comes from zeros near the central point, and therefore we can use the statistics to obtain bounds on the order vanishing of L functions. The n-level density and the n-centered moment are closely related statistics of local zeros of L functions. The shown equation is a theorem about the n-centered moment that we can use for computations. In our work, we generalize Hughes-Miller's n-centered moment theorem to allow n arbitrary test functions. There are two key changes that we made to the Hughes-Miller proof. First, since the test functions are no longer treated as identical, we needed to replace the original combinatorial factor of 2m minus 1 double factorial with every distinct unordered pair of test functions. Since test functions still satisfy the same requirements, the integral generalizes. Secondly, we constructed an auxiliary test function psi and replaced all individual phi's with psi to obtain upper bound on the error term, and we then showed that this upper bound is negligible. In terms of test function optimization, we discovered a new test function phi, which is shown below, that satisfies all restrictions above here and yields better results than the naive test function. We used the improved test function and generalized theorems on the n-centered moment to compute bounds, and we improved the bounds. Typically, after the first few initial papers, subsequent progress is small, usually only slight improvements in later digits. However, we see improvement as early as the fifth order vanishing, and the value of our approach becomes apparent as we look at higher and higher vanishing. For instance, our result is better by almost 6 orders of magnitude at the ranked 500. In conclusion, after generalizing two n-centered moment theorems and exploring test function optimization, we obtained world record upper bounds for order vanishing at the central point. Our results have significant mathematical contributions because zeros of L functions are central to many prominent unsolved conjectures, like the Birch and Swinnerton-Dyer conjecture. Directions for future work include evaluating bounds using higher centered moment, increasing support for test function, and further optimizing the test functions. Thank you.